Computing technology is on the cusp of a revolution. From accurate weather forecasting to efficient traffic routing, from super-fast development of medicines and vaccines, to ultra-secure banking transactions and unbreakable passwords, quantum computing will transform human life as we know it. Paradoxically, even scientists harness the potential of quantum technology. Quantum physics itself is barely understood. As physicist Brian Greene said, if you want to understand or visualize the quantum world, you have to forget everything you think you know. The path to understanding quantum physics started several centuries ago, with scientists seeking the answer to a fundamental question: what is the nature of light? Is it a wave or is it a particle? Waves and particles have very different behavior and characteristics. But is it possible that something can behave like a wave and a particle depending on how it is observed? Let's understand this with an analogy. A tennis ball is like a large particle. Now, if the ball is thrown at you, it will not diffract around you like a wave in a lake. It would hit you because you are in its path. But at the quantum or the smallest level, what is a particle and what is a wave blur into what's called wave-particle duality. That is at the heart of quantum physics. Let's back up a little. In the 1660s, Sir Isaac Newton used a prism to split sunlight into its 7 component colors. But he didn't realize that the relative brightness of those colors held the key to the quantum world. He described the nature of light in his work, published as a book, Optics. He observed that a candle or any other light-emitting substance reduced as it emits light. So he assumed that light is emitted by the candle in the form of particles or corpuscles. He was a pioneer of corpuscular theory of light. In the early 18th century, Thomas Young was studying why the eye changes shape to focus on things placed at a different distance. To understand this, he performed the double-slit experiment. He projected light through a pair of tiny parallel slits onto a screen. But before we experiment with light, let's go back to our analogy of a tennis ball. If the ball's trajectory lines up with the slit, it goes right through and makes an impact on the screen. If it does not line up, then it makes no impact on the screen. If we do this several times, we will have 2 distinct areas of impact on the screen precisely behind the slits. This outcome is consistent with the behavior of particles. Now let's repeat the experiment with a wave of water. As the wave passes the slits, it breaks into many waves. These waves interact as they continue their journey on the screen. In some areas, their interaction is positive, and that makes them stronger. And in others, they interact negatively and become weaker. When these interfering waves hit the screen, they don't leave 2 spots like the tennis ball. Instead, we get what is called an interference pattern. Now that we understand the nature of particles and waves, let's repeat Thomas Young's experiment with a beam of light. And this is where things become fascinating. Young shot a light beam towards a piece of foil. The result of Young's experiment was an interference pattern on the foil, which provided compelling evidence that light had the properties of a wave. So scientists accepted that light traveled in waves. For the rest of the 18th century, physicists turned their attention to describe something called the black body spectrum mathematically. Above absolute zero, every atom and molecule in a body moves around. And as these particles move, they emit radiation in the form of electromagnetic waves. For example, in an electric bulb, The filament glows red as electricity passes through it as a result of heating the filament. As the amount of electricity is increased, the lamp glows brighter and brighter, and the light color changes from red to blue. So there is a relationship between the color or the wavelength of the filament and its temperature. The problem was that the mathematical formula being used at the time to figure out what sort of electromagnetic radiation or light would come out of an object at a given temperature was not fitting the experimental data. Fast forward to 1900. The debate about the nature of light was about to get very interesting. Max Planck turned his attention to this problem. The formula at the time was based on the understanding that particles, when heated, wiggle in every possible way, and theoretically, these variations of these wiggles could be infinite. Max Planck decided to see what would happen if instead of infinite states of wiggling or energy states, there was some minimum and all the energy states were just a multiple of this minimum. And it worked. The Planck's law was able to predict black body spectrum correctly at really high temperatures. That minimum energy is now called the Planck constant. The tiny constant at 6.63 multiplied by 10 raised to minus 34 joules seconds sets the scale of the theoretical length below which the concept of length loses meaning. In a sense, it defines the pixel scale of the quantum world. Planck's constant made the mathematical equation fit the experimental data. Still, the actual theoretical interpretation was left to Einstein to explain a few years later when he discovered the photoelectric effect. Using Planck's constant, Einstein in 1905 discovered the photoelectric effect, which led to the Nobel Award in 1921. He found that when light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened with the light of specific wavelengths. For others, no electrons jumped at all. Einstein was puzzled by this phenomenon. If the light wasn't made of particles, and now it seemed it wasn't made of electromagnetic waves either, then what was it? Einstein formulated a theory combining the two previous theories of light. What if the light was made not of waves or particles, but both? The work of Max Planck and later Einstein led to the discovery that light is made of photons or bits of quantized energy, and that photons can sometimes be described as a wave, sometimes as a particle, and sometimes as either. What determined their behavior was how we observed them. In other words, the reality is shaped by the observer at the quantum level. This phenomenon is called wave-particle duality, or the ability of subatomic particles to exist in two states at the same time. In 1935, Austrian physicist Erwin Schrödinger explained it by a thought experiment famously called the Schrödinger's cat experiment. The experiment presents a scenario where a cat in a box can be simultaneously alive and dead at the same time, and therefore is theoretically in a state known as quantum superposition.
His idea was to explain the weirdness of quantum physics. Actually, if we go to the history, we see that just before this proposed experiment, there has been a unanimous thought or unanimous resolution between quantum physicists that how quantum theory behaves. And what they resolved, which we call as Copenhagen interpretation, was that any quantum system is in a superposition state until it is observed or until it is mixed with the environment. So what Schrödinger proposed, that this kind of interpretation actually can lead to various implications which are unphysical or which are unreal to our everyday observations.
This common sense defying idea opened the gates to the universe of quantum physics. We can all agree that the world we live in today is vastly different from just one generation ago. The futurist Ray Kurzweil wrote in an essay that humans today find it hard to comprehend their future. He argues that technological change today is exponential and that we won't experience 100 years of progress in the 21st century. At today's rate, it will be more than 20,000 years of progress. And in this age of technological innovation, computing power will play a significant role. Innovations in driverless cars, robotics, nanotechnology, artificial intelligence or AI and machine learning, cryptography for secure communications, and many other areas of science and technology will be powered by super-fast computers, faster by orders of magnitude. Quantum mechanics will power these next-gen computers.
Kind of problems which require exploring many possibilities and then finding the best one. A quantum computer is likely to do that problem better than a classical computer because of the fact that this superposition allows you to explore many things in parallel. And then you arrive at the answer a lot faster. I mean, this is a very simplistic picture, and that is why the possibilities are still endless.
The next obvious question is, how do quantum computers work? Conventional computers encode information as a string of binary digits, 0 and 1. In contrast, quantum computers use quantum bits or qubits. Qubits exist in a superposition state, that is until they are measured. Qubits can be both 0 and 1 at the same time. Just like the cat in Schrödinger's thought experiment can be alive or dead until it is observed. For example, let's say you're trying to figure your way out of a maze. You will rule out every possible exit one by one until you find the one that leads you out of it. By contrast, a quantum computer would check out all the escape routes simultaneously and present the right choice instantly.
Let's just build up on this idea of a bit. If you go to 2 bits, there are 4 possibilities, right? 0, 0, 0, 1, 1, 0 and 1, 1. These are the numbers 0, 1, 2 and 3 in decimal written in binary. But a 2-bit system, a classical 2-bit system, will be able to store one of these 4 possibilities. Whereas a 2-qubit quantum system will be able to be in a superposition of all the 4 possibilities at the same time. Now you keep extending this, you go to 3, you have 8 possibilities, you go to 4, you have 16 possibilities, and then it grows exponentially. So by the time you come to even a modest number like 300 bits is still a very small number compared to the amount of memory we have on our phone and USB hard drive and things like that. But 2 to the power 300 is the number of combinations that is possible. A classical 300-bit system will only be able to store one of those numbers, but a quantum system of 300 qubits can be in a superposition of all of these states at the same time. And what is 2 to the power 300? It's roughly the number of atoms in the visible universe. So you can imagine how immense this number is and how it grows very quickly and exponentially, that you have access to this very vast space where computations can be done.
Although quantum computers carry the immense potential for the future, they are already making their mark in some industries. In the field of medicines, quantum computers can mimic the same quantum properties as the molecule they are trying to imitate, thus paving the way for better and cheaper drugs in the future. Quantum computing is also going to have a significant impact on the next generation defense systems. The United States' biggest defense contractor, Lockheed Martin, is already using computing systems based on quantum principles to make sure their weapon system is error-free. Another area where quantum computing offers immense possibilities is cryptography, and secure communications. Cryptography is the science of securing information and transforming messages through codes or texts that are hard to decipher. These codes are called keys or ciphers. When you log in for net banking, fill out an online application for a passport, or carry out any transaction on an e-commerce site, your information is protected, transforming it into an unreadable format or encrypted to prevent any misuse. Today's cryptographic systems rely on complex algorithms and the difficulty of factoring products of large prime numbers. Quantum computers, owing to quantum algorithms and enormous computing capability, can break these encrypted communications relatively easily. So once quantum computers become common, what will it take to keep our data safe? The answer lies in quantum encryption, in which security is maintained using the principles of quantum mechanics. Any attempt to break into the system invariably affects the system, alerting the legitimate parties about the eavesdropping.
We use single photons for the communication and some parameter of single photon, for example polarization or time of arrival or maybe some other parameter to encode the bits. Now when single photon is sent from one party to another and someone tries to intercept in the system, he will measure that single photon. So it can be measured only by the eavesdropper or by the receiver, but it cannot be by both. So what he has to do, he has to prepare another single photon in order to take part in the key generation process, and that single photon would not be as the original single photon because that parameters were not known to the eavesdropper. So he has only got some partial information about it, and because of that whatever error is introduced into the system, that is actually noticed by these two parties.
Countries and companies want to be the first to exploit breakthroughs in quantum mechanics to gain a competitive, commercial and strategic advantage. In 2009, the global quantum computing market accounted for about $90 billion. According to some estimates, it will grow at a projected annual rate of 29% through 2026. In this backdrop, what is India's strategy to develop indigenous solutions based on quantum mechanics? India's quantum mission is making steady progress over the past few years in terms of merging theoretical aspects of quantum mechanics with experimental projects by ramping up the expertise and facilities available in the country.
One of the most important applications of a quantum computer would be to model nature, because nature works on the laws of quantum physics, and if we understand how nature works, then basically the possibilities are endless. Let me give a few examples. You're designing a new medicine. A medicine is basically composed of some molecule. A molecule is composed of some atoms, right? And atoms behave the law of quantum physics. So if I can represent this model properly, efficiently, so that the full laws of quantum mechanics are apparent, then it allows me to understand how this molecule will behave, what kind of properties it can have, how it might interact with other medicines, for example, and all of this can be done on a computer. The moment you say molecule, then basically the whole realm of material science comes into the picture. Maybe tomorrow we want a more energy efficient battery or a cleaner fuel. All of these can now be understood from the basic quantum physics laws which govern how these molecules functions, and you could even invent new molecules. But a quantum computer would eventually allow you to do something at that level, where you can really do all of these calculations in an efficient fashion, and then once you understand it, then you can go into actual production of those chemicals or materials.
There are several other applications, for example, which are more often called as intractable optimization problems, such as traffic optimization or database search, financial modeling, weather forecasting. So these are some of the key areas where quantum computers can actually be the game changers.
India is rapidly gearing up to build quantum computers and join the ranks of Western countries. In 2019, the Department of Science and Technology set up Quantum Enabled Science and Technology, or QUEST, to make investments in infrastructure for promoting research in the field of quantum science and technology.
Now the QUEST, basically the first thing it did is did the capacity mapping in the country. We identified more than 50 groups, mostly young scientists, who are working in the area of quantum, but we also need to seed the capacity in quantum experimental research. So these more than 50 groups that were identified are being supported under the QUEST program.
The nurturing of the PhDs in this field is very much essential. So there is around 100 PhD scholars who are working for the projects, and at the same time they will be getting their PhDs also. So that way down the lane, if you look at it, maybe 3-4 years, we have 100 core scientists coming out from this QUEST program.
The main goal for QUEST is to achieve, within the next 10 years, the technical capacity to build quantum computers and communication systems comparable with the best in the world. The goal received a significant shot in the arm in early 2020, with the government allocating 8,000 crore rupees in its latest budget towards national mission on quantum technologies and applications.
Quantum technology is opening up new frontiers in computing, communications, cybersecurity, with widespread applications. It is expected that a lot of commercial applications would emerge from theoretical constructs which are developing in this area. It is proposed to provide an outlay of 8,000 crores over a period of 5 years for the national mission on quantum technologies and applications.
The funding boost will ensure that India too can make significant contributions in quantum technology. Under the aegis of the Department of Science and Technology, the mission will also help prepare next-generation skilled human resources, boost applied research, and also encourage entrepreneurship and startup ecosystem development.
Both the systems that generate knowledge, which is relevant, which is with quality, which is profound, that system has to work with industry, and it has to work with the government. So many government agencies and ministries would have interest in these technologies and products. At the same time, you have to work with the startups. So it is what you call the triple helix of knowledge, and we would implement it totally with flexibility given for scientific work which is required.
So this is the niche area, emerging area, huge potential, therefore is a huge opportunity for the startups. Therefore we are giving more stress for the young entrepreneurs to come on board, pick up these ideas, and then scale it up and become the unicorns in coming days.
Imagine a future where quantum sensors will be able to prevent floods by predicting weather systems, monitor the water table more accurately, and help in the discovery of oil and natural gas reserves. A future in which our telecommunications and financial infrastructure will be more robust and secure than ever before. And our cities will be able to predict demand for its infrastructure in real time and allow smarter use of energy and water resources, enabling higher environmental standards and efficiency.
The possibilities from a quantum computing technology are so enormous and also have strategic importance. And that makes it equally more important that we do it now, and we have to do it very, very quickly, because the longer we wait, the more we will have to catch up.
I am expecting overall another 10-15 years. I think slowly the countries will move towards the quantum-based communication and computing. And India has got a very good opportunity, both in terms of the talent, the infrastructure, and applications.
As we know that we have Digital India campaign by Government of India, where everything is online, everything is digitally done. So that security At the moment it is through classical cryptography, but at the moment when there will be sufficiently powered systems to break those codes, one needs to rely on quantum securities such as quantum key distribution for those purposes.
I am very hopeful, I am very optimistic that this would indeed bring value to India, to our society, to our industry in remaining competitive.
The possibilities led by quantum revolution are endless. From finding answers to problems that surround our material world, to unraveling the layers of human consciousness, and even opening the doors to the prospect of having multiple worlds. Quantum mechanics is the key that defines our existence in this universe, our past, present, and future. Because in the end, we are all nothing but atoms.